The next concept we need to consider in our electrochemical explorations is that of electrical potential, and fundamentally what it is. So we've seen potential many times before. We've considered thermodynamic potentials, we've considered chemical potentials, and in first year we considered the Lennard-Jones potential. So I'm going to look at Lennard-Jones potential because we had a key definition with it. That definition was the work done to move molecules from infinity to a point of interest. So whenever we had our molecule, we'd start at an infinite separation and look at how much work we would need to do to bring it to a particular position. If the potential was negative, that meant that we were getting energy out of the system, and if it was positive, that means we had to put energy in. So if you think about moving a molecule, it will freely fall into this minimum because that releases energy, but then we have to put energy in to drive it up this slope to squeeze molecules further together. The key definition is that potential is defined at zero, at infinite separation. So we have a negative potential, which is our minimum, and we can have a positive potential where we're putting more and more energy in. Electric potential has a very similar definition. It looks at the work required to move a unit positive charge from infinity to a point of interest. So if we have a positive charge at infinity and we want to bring it close to a positive electrode, we have to put energy in. That means this electrode has a positive potential. We have to do work to bring a positive test charge close to it. Again, it's defined at zero at infinite separation, so everything is based on that. And we can plot our Coulombic potential in a very similar way as we have for the Lennard-Jones. The anode has a positive charge, so we need to do work to overcome the repulsion for a positive charge. We need to do work on that positive charge to bring it close. Therefore, we have that high potential. We run into a few conceptual issues, however. When we start to consider potential versus electron energies, we start to think things becoming a little bit confusing because potential is fundamentally related to a positive charge, but our electron is negatively charged. Therefore, if we have a high positive charge on our electrode, we have a high potential. However, if we have a high positive charge, it has a low electron energy because it's attracting the electron. Vice versa, if our electrode has a high negative charge, it has a low potential because there's less work required to bring a positive charge towards it. However, a high negative charge means we have a high electron energy, and we need to do work to overcome that repulsion. One way to picture this is when an electron is surrounded by positive charge. All those positive charges have very high potential, but they are serving to lower the electron energy because they are stabilizing it. A potential difference, therefore, is the difference in potential between two areas. That's all we're looking at, but you're familiar with the term potential difference. But we need to understand it rigorously in terms of our definitions. It is simply a statement of a difference in charge because each charge carries a potential and each area will have that different potential. Any charge species at all, whether it's an electrode, whether it's our ions in solution, they can all cause a potential difference. Wherever there's a potential difference, a charge species will migrate. They'll move through that potential difference to minimize their potential, fundamentally lowering their electrochemical potential. This electrochemical potential carries a symbol mu bar. It is absolutely related to the chemical potential that you've seen before, which is why it uses a very similar symbol. Considering the fact that charged particles move to minimize their electrochemical potential, well, let's think about this in terms of the chemical potential. If we have a standard chemical potential, we can simply work out the electrochemical potential standard. We can simply work out the standard electrochemical potential by considering the charge on the ion with the Faraday constant and the localized potential phi. So it's related to this charge and the potential in that medium there. So using this equation, we can start to visualize what's going on. So if we think that our chemical potential at any point is equal to the starting chemical potential or starting standard chemical potential, if we're not under standard conditions, we can simply find the electrochemical potential by using our starting chemical potential for a given situation. If you remember from year one that our standard chemical potential can be found from the sum of the actual chemical potential and the activity of the solution. Thinking about these chemical potentials, electrochemical potentials, they're all fundamentally related to free energies. So let's think about what's going on at the interfaces. Because the interface is where all the good stuff happens. So understanding that interface is really important as well. So let's think about energy level diagrams. These are schematic diagrams to show the energy of the interface. By convention, the solid is shown, or the electrode is shown on the left. So let's think about the electron energy in the solid. Well, the solid electrode has a lot of electron energy levels altogether existing in something called a band. The highest energy of this band is known as the Fermi level. We don't need to worry too much about the theory of this at the moment, but the Fermi level is simply the highest filled level of that band. So that's the area where the electrons are going to come from, the energy level from which we will liberate electrons at the electrode. If we now look at the electron energies in solution, these are usually single molecules, so they have discrete energy levels. So we have a lot of different energy levels in solution, but we'll only consider the frontier energy levels to start with. If we consider an electron present in this energy level, remember that electrons will move to try to minimize that energy. So at the moment, we have energies in a higher level in this Fermi level, and we have an available space in solution, which means that the electron can move from the electrode into solution. So it's minimizing its energy. When this happens, we have the solvated species being spontaneously reduced. Okay, so it's picking up an electron from the electrode and therefore being reduced. Let's consider a slightly different situation. If the solvated species has a higher electron energy than the Fermi level, the electrons will still move to minimize energies, but this time the electron will move from the high energy in solution and it will move to the electrode, which has a Fermi level at a lower energy. This means in this case the solvated species is spontaneously oxidized. It loses its electron to the electrode. In both cases we've transferred a charge, whether we've transferred the charge due to spontaneous oxidation or whether we've transferred a charge due to spontaneous reduction. This spontaneous process creates a potential difference and fundamentally causes electron transfer when we connect the circuit. When we think about electrodes, we think about applying a potential difference to them. The position of that Fermi level can be adjusted by applying a potential to the electrode. So whatever potential we apply will change the energies of the electrons in that electrode. If we apply a positive potential, it has the effect of lowering the Fermi level. Remember, we're surrounding the electrons by more positive charge, making them more stable, lowering their energy. Conversely, a negative potential is removing positive charge. It makes the electrons less stable, so it raises that Fermi level. So let's picture what's going on. If we raise the potential, we add positive charge. This build-up of positive charge has the effect of lowering the electron energy in that electrode. So the Fermi level drops. What this means is the Fermi level is now at a lower energy level than the highest energies of electrons in solution, and that electron can move and drive spontaneous oxidation. If we think about the opposite case, if we lower the potential, we're removing positive charge from the electrode. If we remove the positive charge, the electrons are destabilized, and that raises the electron energy in the electrode, which raises the Fermi level. So in this case, we now have electrons in the electrode which are now at a higher energy, and they can now move from the electrode into solution. And this drives the reduction of the solvated species. Just to quickly summarize potential, remember that everything is respect to a positive test charge. So we have this double-headed arrow going on. If we have a high potential, we are adding positive charge, which means we are removing negative charge. Fundamentally, this stabilizes electrons and lowers the electron energy. For low potential, we've removed positive charge, which effectively means we've added negative charge, and we've raised the electron energy. So removing positive destabilizes electrons, adding the positive stabilizes electrons. So this causes the movement of the Fermi level. And we can drive our reduction and oxidation accordingly. Let's now look at the energies of the interface. Potential can fundamentally change the electron energy, as we've discussed. This creates a potential difference across that interface. But how is that potential difference distributed? How this charge is distributed affects the kinetics of what's happening at the electron, whether we're looking at electron transfer of the electron across the interface, and how the ion gets to the surface to be reduced and oxidized. And all of these factors must be considered. Let's firstly look at the charge distribution at the interface. So we're going to zoom in at the microscale. We're going to zoom in into a small part of that electrode. We're going to say that the metal electrode has a net positive charge. We're going to call it QM, so the charge in the metal. So let's populate this with charges. But we're going to now consider the ionic atmosphere model. We're going to consider solvation of that electrode. So as we add the positive charges, we have to populate the surrounding solution with negative charges as well. And we can expect this metal to be solvated, as it were, with an equal and opposite charge, QS, charge in the solvent. The interface zone that we've highlighted must be neutral. It has no charge. But what we see is we have a gathering of ions at the surface, but once these have fully occupied the surface, the only way we can get the extended charge needed to balance the charge on the metal is to have them loosely associated outside. So the interface zone we're looking at is neutral, has no charge, so Qm is equal to negative Qs. And we can see we have two distinct modes of solvation, as it were. We have this rigid attachment to the surface, which is an ion pair type mode, and we have something loosely bounded to the interface. This is a bit more of the ionic atmosphere mode. And in this area we allow for thermal motion. Let's zoom out a bit, let's look at the overall structure of the interface. We have two distinct zones present in this interface. So in order to visualize this, let's add a few more ions to visualize the structure. So let's populate the metal with its charges. So we filled up the metal surface with positive charge. Let's start balancing this charge with anions. So for ions held directly at the surface, these are rigidly held in position, and their centers define something called the inner Helmholtz plane. This is simply a construct to visualize the distribution of charge. Okay, we don't quite have enough anions to balance the charge here, so we need to populate the rest of the space nearby with anions to balance the charge on the metal. So again, considering the same ionic atmosphere model, we start populating with anions, but remember there's thermal motion, so there's going to be cations in here as well. The important thing is that the overall charge in this particular zone must be equal to the charge in the metal. So this defines another area of the solvent. Outside of this area, there's no excess charge. So all of the anions and cations balance, and we have an equivalent charge from the cations as we do from the anions. So this is the structure of the bulk solution. So we want to now look at how the potential varies across that interface. So we've defined two regions of space, and this is known as a double layer, or something called a diffuse double layer, because we have a diffuse layer in this region. It refers to the two sets of charges that we're looking at. We're firstly referring to the rigidly held charges at the inner Helmholtz plane, which are fundamentally ion paired to the surface, but we then have the remaining charge, excess, which is subject to thermal motion. And we would expect to have more of the anions closer to the electrode than we do further away from it. And this means that the potential varies with distance from that surface. So if we have a variation, we're immediately thinking we want to try and visualize this with a graph. So let's plot how the potential varies with distance from the electrode. As we look at this, we find that we have a very steep decrease in the potential to the inner Helmholtz plane. So this is the distance from the surface to the center of the rigidly bound anions. And then we have a more gradual decrease to get to the final potential of the solvent. So this potential of this bulk solvent here. So this is a way of visualizing how that potential varies with distance. In summary, remember that potential refers to the energy of a positive test charge. A high potential gives us a low electron energy, while a low potential gives us a high electron energy. So think about what's going on. This is a potential source of confusion, but remember that if we have a high potential electrode, that means we've added positive charge to it, which is stabilizing the electrons. By applying the electrode potential, that allows us to control processes. So if we lower the Fermi level, if we apply a positive potential, it lowers the Fermi level, which will drive spontaneous oxidation. If we lower the potential, we're removing positive charge, remember, that raises the electron energy, and that has the effect of driving spontaneous reduction at the electrode. And finally, thinking about that potential at the electrode interface, that charge distribution varies with distance. And fundamentally, this affects the solution potential that we want to consider.